Welcome back. Today we're looking at Section 8.7, Indeterminate Forms and L'Hopital's rule. So first, setting the stage, this has to do with limits. So if a limit produces either the form 0 over 0 or infinity over infinity, we can apply the rule. The limit as x approaches c of f of x over g of x. So this was found to either be 0 over 0 or infinity over infinity. If that's the case, then this is equal to the limit as x approaches c of f prime of x over g prime of x. So notice this is not the quotient rule from your derivative days. It's just saying differentiate the top and differentiate the bottom and see if we have a limit that can be found easier. So first we'll check to see some cases where it does or does not apply. So we'll do the limit as x approaches 1 of x plus 2 over x plus 6. Well, if we try that, we just get a 3 up top and a 7 on the bottom. So this one is no, we would not use the L'Hopital's rule. Not only would we not have to, because we have found the value, applying L'Hopital's rule in this situation would give us an incorrect result. Notice the derivative at the top would be 1, derivative at the bottom would be 1. 1 over 1 is worth 1, not worth 3/7. So we do have to make that check that we have the indeterminate form in order to be able to use this. All right, so the next one, same question, does L'Hopital's rule apply? This time we'll do the limit as x approaches 4, x squared minus 6x plus 8 over 5x minus 20. So if I put a 4 up top, we've got 16 minus 24 plus 8, that's a 0. Downstairs, 20 minus 20 is 0. So 0 over 0, yes, L'Hopital applies. So if we apply L'Hopital, this becomes the limit as x approaches 4 of 2x minus 6, so the derivative of the trinomial at the top over the derivative of the bottom, 5. And then we just check it again. So upstairs we have 8 minus 6, 2. Downstairs we have a 5. This is one of the examples that we can confirm algebraically. You've already been able to do limit problems like this from back in your early in your Calc 1 days. They would have approached this as just a factoring problem. So limit as x approaches 4 of factoring the numerator, x minus 4 by x minus 2. Downstairs, factor the 5. And just cancel out the 1. So 4 minus 2 is 2. There's our 2/5 gotten a different way. All right. So next up, we get to play with one of our transcendental functions. We'll do the limit as x approaches 0, e to the 7x minus 1 over 5x. So e to the 0 is 1. 1 minus 1 is 0 at the top. 5 times 0, 0 at the bottom. So we do have the 0, 0 over form. So yes on L'Hopital's rule. You do have to check for that each time. So now we have the limit as x approaches 0 of 7e to the 7x over 5. So e to the 0 is still 1, so we have 7/5 then as our limit. So next up, we'll try the limit as x approaches infinity. Natural log of x to the 8th over 7x. So natural log of infinity to the 8th, infinity to the 8th is infinity. Natural log of infinity is still infinity. So we have infinity at the top. 7 times infinity is infinity at the bottom. So L'Hopital's rule may be used. So then this is the limit as x approaches infinity of differentiating the top. We can turn that 8 into a factor, and derivative of natural log is the reciprocal of x. So 8 over x up top, 7 at the bottom. So the limit as x approaches infinity of 8 over 7x. So now as x goes to infinity, our denominator goes to infinity, but the numerator stays still. 8 over an infinitely large number approaches then 0. Okay, next one. More fun with exponentials. So we'll do the limit as x approaches infinity. 4x cubed upstairs, e to the x squared downstairs. So at the top we have infinity, bottom also infinity. 4 times infinity cubed, e to the infinity squared. Infinity over infinity, so L'Hopital's rule is appropriate. So now we have the limit as x approaches infinity of 12x squared over 2x e to the x squared. Now we do have a little bit of cleanup we can do there. Limit as x approaches infinity of 6x over e to the x squared. Here we still have the form of infinity over infinity, so we can apply L'Hopital's rule again. There's not really a rule that says you can't reapply L'Hopital's rule. If your limit still produces 0 over 0 or infinity over infinity, you're free to once again use L'Hopital's rule. So now we have the limit as x goes to infinity. Derivative of 6x is just a 6. Derivative of e to the x squared is 2x e to the x squared. We can do a little bit of cleanup on that. So then we have the limit as x goes to infinity of 3 over x e to the x squared. So this is then basically 3 over infinity, which is 0. All right, so the next one, a little bit more work to it, but more interesting example. So we're going to do the limit as x approaches infinity. 1 plus 1 over x to the 5x. So this one we basically have an indeterminate form of 1 to the infinity. So here we can use sort of a placeholder variable, a dummy variable. So we're going to let y equal the limit as x approaches infinity of 1 plus 1 over x to the 5x. We have this exponent in the variable. As you hopefully suspect, we're going to use logarithms to knock it out of there. So we'll do natural log of both sides. So natural log of y is natural log of the limit as x approaches infinity, 1 plus 1 over x to the 5x. Now we can use properties of logarithms in here as well. So natural log of y is the limit as x approaches infinity of 5x natural log 1 plus 1 over x. So just properties of logarithms. Natural log of this and of this limit is the same as doing the limit of that natural log. Okay, so we can grab a 5 here. So natural log y is 5 times the limit as x approaches infinity, x natural log 1 plus 1 over x. So now we do have the appropriate form. Let's see. Yeah, we'll do a little rearranging. We're going to change the look, but not the value. Natural log of y is 5 times the limit as x approaches infinity. Notice the L'Hopital's rule, we want a fraction involved. So what we can do is move this x to the denominator. So we can call this upstairs natural log of 1 plus x to the negative first, downstairs x to the negative first. So as x goes to infinity, reciprocal of x goes to 0, natural log of 1 is 0. And 1 divided by something infinitely large also goes to 0. So it is appropriate to use L'Hopital's rule on this version of it. So the natural log of y is worth 5 times the limit as x goes to infinity. And we differentiate this. So natural log of 1 plus x to the negative first, so that would be negative 1 x to the negative 2 over 1 plus x to the negative 1. So that's our derivative at the top. Derivative of the bottom, negative 1 x to the negative 2. So the natural log of y is worth 5 times the limit as x goes to infinity. So a little bit of cleanup here. We have negative 1 over x squared over 1 plus 1 over x. And we're dividing by negative 1 over x squared. If you want, you can put it as over 1. So divide by that, multiply by the reciprocal, and the negative 1 over x squareds will drop. So natural log of y is 5 times the limit as x goes to infinity. So those guys are now just 1s. So 1 over 1 plus 1 over x. So as x goes to infinity, this term drops to 0, but the rest of it becomes a 1. So then natural log of y is 5 times 1, or just 5. So e to the 5th is worth y, and then that is our limit. Remember, we called y our original limit in the original problem. So this is our limit e to the 5th. So this did involve a little bit of manipulation, a little bit of simplifying, and of course our buddy L'Hopital's rule on this step. This is where we used L'Hopital back here, going from here to here. Okay. Alright, so next up, we get to play with y equals the limit as x approaches 0 from the right of sine of x, quantity raised to the x. So sine of 0 is 0. 0 to the 0 is one of our indeterminate forms. So like before, if I want to get that variable out of the denominator, it's another example where we go to logarithms to play with that. So natural log of y is natural log of the limit as x approaches 0 from the right, sine of x, quantity raised to the x. A little bit of rearranging. Natural log of y is then limit as x approaches 0 from the right hand side of the natural log of sine of x, and x is now a factor, not an exponent. Again, we can use a little bit of sort of rearranging just to satisfy L'Hopital's rule, make it look like a fraction by dropping this x into the denominator and making it 1 over x in a denominator. So natural log of y, limit as x approaches 0 from the right, natural log sine of x upstairs, reciprocal of x downstairs. So sine of 0 is 0. Natural log of 0 goes to infinity. 1 divided by 0 also goes to infinity. So this is an infinity over infinity form. That tells us that yes, L'Hopital's rule may be used. So hang on to natural log of y on the left-hand side and use L'Hopital's rule on the right-hand side. Natural log of u is u prime over u, so derivative of sine is cosine. Over we keep the sine x. And differentiating 1 over x, so that's x to the negative first, so negative 1, x to the negative 2. And we're still looking at a limit as x approaches 0 from the right. So we can do a little bit of simplifying on here. Get rid of the whole fraction within a fraction thing and say that the natural log of y is the limit as x approaches 0 from the right of negative x squared cosine x divided by sine x. Now if we let x go to 0, we have 0 squared is 0, opposite of 0 is still 0, cosine of 0 is 1, 0 times 1 is 0, so I have 0 up top and 0 at the bottom. So we once again have the 0 over 0 form. So we are free to use L'Hopital's rule again. So natural log of y is equal to limit as x approaches 0 from the right. We have negative 2x cosine x plus opposite of x squared times minus sine x over cosine x. So this was applying L'Hopital's rule and the product rule upstairs, derivative downstairs. Let's see, so I have zeros across the board there and 1 at the bottom. So natural log of y is 0 over 1, which is 0. So e to the 0 is equal to y. E to the 0 is 1. Therefore, y is equal to 1. So the limit as x approaches 0 from the right of sine x over x is worth 1. All right, so then our last example of the section. Limit as x approaches 2. It's a messy 2. That is a 2 nevertheless. 1 over x squared minus 4 minus square root of x minus 1 over x squared minus 4. So right now we have 1 divided by 0, which is infinity. And we have 1 divided by 0, which is infinity. Infinity minus infinity form. So one thing we can do is just put this sort of under one roof and make it into a 0 over 0 form. So we'll make this the limit as x approaches 2. 1 minus x minus 1 to the half over x squared minus 4. Now we have 1 minus 1, 0 at the top. 4 minus 4, 0 at the bottom. So L'Hopital's rule is now appropriate to use. So this is now the limit as x approaches 2. And our derivative of a constant 0, so negative 1/2 x minus 1 to the negative 1/2 times 1. And downstairs our derivative 2x. A little bit of cleanup on there. Limit as x approaches 2. Let's see, so we have negative 1 at the top. 4x square root of x minus 1 at the bottom. Now if we let x go to 2, we have negative 1 at the top. Then we have 8 times square root of 1. So negative 1/8. And that is our limit. So if you see a form like this, try to still turn it into a 0 over 0 form or an infinity over infinity form. All right, so in 8-7, suggested problems, 5 to 61, the odds. 83 to 87, also the odds. And a little hint on number 31. Try 2 iterations of L'Hopital's rule, and that will let you see why you need a different method on that one. 31's going to need a different method. All right, any questions, please get in touch with me. Otherwise, I will see you next time. Stay safe out there.